In a previous model titled Introduction to Multiple Linear Regression Part 1, we had discussed the fitting of a multiple linear regression and also the interpretation of the regression parameters involved in such model. In this module, we will discuss the inference. We will discuss how we can test the goodness of fit of a multiple regression model and also how we can test the significance of each independent variable used in the model separately. This current model is dedicated to the discussion of the different tests in connection to multiple regression model. This module is named Introduction to Multiple Regression Part 2. Let me first give you a brief overview of this lecture. In this module, we will discuss the different types of tests that we perform in connection with regression models, the overall F test, the partial F test, and the test of individual regression coefficients. And we will illustrate these and we will then discuss 3 different variable selection techniques used in multiple regression models. First, let me begin by discussing the 2 types of tests in connection with regression models. The 2 different F tests that we can perform are the overall tests of significance and the partial F test. In the overall test of significance, we test the goodness of fit of the overall regression model. So, in case our regression model is given by y equals beta naught plus beta 1 x1 plus beta p xp, where x1, x2, xp, in the overall test of significance, we test for the goodness of fit of the overall regression model. So, suppose the regression model that we fit is y equals beta naught plus beta 1 x1 plus beta 2 x2 plus beta p xp, where x1, x2, xp are the predictor variables and beta naught, beta 1 and beta p are the regression coefficients. Then we test whether all the predictor variables included in the model, this complete model, is significant or not. However, in partial F test, the F test is frequently seen as a model comparison tool, which tests the hypothesis that the R square for the more complex model is significantly larger than the R square for the model that contains lesser variables or the reduced model. Now, in overall F test, considering the general case where we have k minus 1 explanatory variable, for the overall F test, the hypothesis in words is that the model has no explanatory power at all. Of course, we hope to reject the null hypothesis, because if we fail to reject this null hypothesis, it would mean that all the explanatory variables that we have used in the model are insignificant and of no use. So, we wish to reject the null hypothesis and conclude that the model is statistically significant. In multiple regression model, however, there is a difference between the roles of the F and T tests. In multiple regression, we use F test to test the joint explanatory power of all the variables, or in other words, to perform the overall test, while the T tests are used to test the individual explanatory variables. So, in case of overall F test, the null hypothesis can be mathematically written in the form of H naught, where beta 1 equals beta 2 equals beta k equals 0, is tested against the alternative hypothesis that at least one beta or at least one regression coefficient is not equal to 0. The test statistic for testing the overall test of significance of the model is given by F equals SSM divided by k minus 1 over SS residual divided by n minus k, where SSM is the sum of square due to the model and SS residual is the sum of square of residuals. And the respective degrees of freedom are given by k minus 1 for sum of square of model and n minus k for sum of square residuals. We can also write the formula for the test statistic as F equals SSM over SS total divided by k minus 1 over SS residual divided by SS total divided by n minus k. We are dividing the sum of square model and the sum of square of residual by the sum of square total. The reason we wish to do this is, by definition of R square, we know that the ratio of sum of squares due to the model and the total sum of square is R square. Hence, we can write the formula for test statistic in terms of R square, and it is of the form R square divided by k minus 1 over 1 minus r squared divided by n minus k. Since the test statistic can be written in terms of r square, we can write the null hypothesis as h naught and r square equals 0 tested against the alternative r square not equals 0. The term r square is called the coefficient of determination in case of regression model with more than one explanatory variable. When there is only one explanatory variable in the regression model, that is, it is a simple linear regression, then the coefficient of determination is simply the square of the correlation coefficient, that is, lowercase r square. Now, second type of testing can be done in connection with multiple linear regression, that is, testing of nested models. By nested model, we mean comparing two models where one model contains certain number of parameters and another model which can be considered as a model nested in the first one contains number of parameters or number of predictor variables less than the first model. The partial F test that we have mentioned is a general procedure for generating partial F test on a nested sequence of model. Consider a sequence of J models denoted by Mj, where lowercase j goes from 1, 2 to uppercase j. Suppose model Mk includes k explanatory variables, and model Mj is a special case of model Mk where Mj contains less number of predictor variables, which means some terms in model Mk have coefficient 0. Model Mj is then nested within model Mk, and we say that the set of model is a nested sequence. Now we would like to test the performance of the nested models. In that context, if we define Tj and Tk respectively as the number of terms including intercept term in models Mj and Mk, we define Ssj to be the sum of squared residuals for the model with less number of terms, model Mj, and Ssk, the sum of squared residuals for the more complex model Mk. The respective degrees of freedom then are given by n minus Tj and n minus Tk. To statistically compare the model Mj against model Mk, we compute the partial F statistic as follows. The test statistic F is given by the ratio of the difference of sum of square of residuals and the sum of square residuals of the more complex model K. So, as a numerator, we have the difference Ssj minus Ssk divided by Tk minus Tj divided by the denominator, which is Ssk over Tk. This test statistic follows an F distribution with degrees of freedom Tk minus Tj and Tk, and we find the critical value and the p-value and check whether the model which is more complex is significant or the one which has less number of predictor values is more significant. A third type of test that can be performed in connection with multiple linear regression is testing the individual regression coefficients. The hypothesis test about individual regression slope parameters can be mathematically written as null hypothesis beta 1 equals 0 tested against alternative h1 such that beta 1 not equals 0. And for the kth slope parameter, we can write h naught such that beta k equals 0 tested against the alternative h1 such that beta k is 0. The test statistic for testing individual regression coefficient is a t statistic with degrees of freedom n minus k plus 1 given by bi divided by standard error of bi, where bi is the estimate of the corresponding regression coefficient. Now, trying to fit a multiple regression model using R, and I will demonstrate it using the anesthesia dataset. The dataset here we have says that during certain surgical operations, the surgeon may wish to lower the blood pressure of the patient by administering a drug. After the surgery is over, the return to normal of the blood pressure depends on the dose of the drug administered and the average systolic blood pressure reached during surgery. A surgeon wishes to study the relationship between the dose of a new drug, the average systolic blood pressure during the operation, and the time for the blood pressure to come back to normal after administration of the drug has ceased. To that end, the surgeon connects data, and the three variables that we have in our data set is log of dose, blood pressure during surgery, and the recovery time required. And we will fit a multiple regression model to this data set using time as the response variable and log of dose and BP during surgery as the two predictor variables. In order to fit a multiple regression model, we will use the LM function in R. We define recovery time as the dependent variable y, and the two independent or explanatory variables are log dose x1 and blood pressure during surgery x2. Here is the R code for fitting the multiple regression model. Before we fit the model, we first read the three variables into R and put them in a data frame and call it anesthesia. And then using the LM function, we fit the model where time is used as the response modeled on log of dose and BP during surgery. We first take a look at the analysis of variance table after fitting this model. In the analysis of variance table, we have the sum of squares corresponding to the two predictor variables and the p-values. And we can look at the summary of the output from R after fitting the LM function. The summary provides us with the estimates of the coefficients of log dose, blood pressure during surgery, and intercept along with their standard errors and the corresponding p-values. So for alpha equals 0.05, when we look at the p-values, we can see that both log dose and blood pressure during surgery are significant predictor variables in this model. After we obtain the estimates of the coefficients, we can write the regression equation comprising of both the explanatory variables as recovery time equals 21.94 plus 10.59 times log dose minus 0.73 times blood pressure during surgery. Now, the value of the F test statistic from the R output is given by the value 7.255 and the corresponding p-value is 0.001712. This p-value provides evidence of the existence of a linear relationship between the response and the two explanatory variables. In other words, this p-value is used to perform the overall F test to test whether the explanatory variables, both the explanatory variables, perform well in the model. And by looking at the p-value for alpha equals 0.05, we can say that yes, the model that we have fitted performs well. Now we have just seen an example where we have included the two variables, the two predictor variables, blood pressure during surgery and log of dose as the two predictor variables. But in reality, most of the time we have multiple numbers of explanatory variables and we need to decide on which explanatory variables are significant and which ones are not. After we decide on which explanatory variables are significant, we usually discard the ones that are insignificant instead of leaving them in the model and increasing the number of parameters. One of the difficulties in fitting a multiple regression model is thus the selection of the potentially significant predictors. Although this problem can be overcome with the use of modern computing power. There are three different methods of selecting models that we will discuss here. They are forward selection, backward elimination, and stepwise regression method. Let us first discuss the forward selection method. In forward selection technique, we first fit a model that has just the intercept term and no explanatory variable. In the next step, we add the explanatory variable with the highest correlation coefficient with the response in the model and test whether this explanatory variable is significant or not by looking at the p-value. If the p-value tells us that this explanatory variable is significant, we leave it in the model and then move on to the next predictor variable, which has the second highest correlation coefficient with the response variable. And after we add this explanatory variable in the model, we now test whether this variable is significant or not. If it is significant, we leave it in the model and then move on to the third variable. And we continue the process until there is no more predictor variables that are significant that can be added to the model. The next method that we can use is the backward elimination method. In this method, we start with all possible predictors included in the regression equation. We then single out the explanatory variable that has the highest p-value or the most insignificant explanatory variable, and we remove it from the model and then fit the remaining explanatory variables in the model and fit this dataset using LM function. Next, we go through the same steps of singling out the explanatory variables that have the highest p-value or are the most insignificant and remove them from the model and continue the process until we arrive at a stage where the explanatory variables that are included in the model are all significant. The third method that we use is the stepwise regression method. This method works like the forward regression, except that we examine at each stage the possibility that a variable entered at a previous stage has now become superfluous because of additional variables now in the model. In other words, just like in forward regression, we add explanatory variables into the model. However, in forward selection method, once an explanatory variable is added in the model, it is never taken out. But in stepwise regression, suppose we add an explanatory variable to the model, and later when we add several other explanatory variables and the first one happens to now become insignificant, then there is a chance of removing the ones that are now insignificant and leaving only the variables that are significant in the final model. Next, let us discuss the automatic sequential testing of single terms. Because I have explained how to fit multiple regression models using R, I would like to discuss the automatic sequential testing of single terms that is performed by R. R automatically performs a sequence of term-by-term tests on the terms in your model, in the order they are listed in the model specification. In R, as we have seen in the previous module, we use ANOVA command on the single full model. We can also show that the order of testing matters and significance level for a term's model comparison test depends on the terms entered before it. Let me illustrate that with an example. For example, let us take a look at the kids dataset that we have seen in the first module of multiple regression introduction. Our model was given by weight modeled on height and age on the kids dataset in that order. After we use the LM function in R to fit this model, we obtain the R output, and from the analysis of variance table, if we look at the p-values corresponding to height and age at alpha equals 0.05, we see that height is significant whereas age is not. Next, if we try to fit a model with the same two variables, height and age, in the kids dataset, but in reverse order, R will test the terms with sequential difference tests. So now we use the LM function to fit the model weight on age and height, where we first put the variable age and then we have variable height. After we fit this model, when we look at the ANOVA table after fitting this model, we can see that the p-value corresponding to age is 0.0008 and for height it is 0.0218. At alpha equals 0.05, both age and height are significant. However, if we look at the p-value of height as compared to the p-value of height in the previous model, we can see that the p-value has increased manifold. In plain terms, we can say that height is now less significant when entered after age because age can predict much of the variance predicted by height. Hence, height has much less to add after age has been already used as a predictor variable. Now let us look at the summary of the fitted model. We have fitted the model with weight as the response and age as the first predictor variable and height as the second predictor variable. In the previous two ANOVA table, we have seen that when height is added as the first predictor variable, it is much more significant when it is added as the first predictor variable than when it is used as the second predictor variable added to the model after age. Now let us look at the summary of the fitted model. If you look at the estimates of height and the corresponding p-value, we can see that the p-value is 0.0218. Now the model fitted was weight modeled on age plus height in R. If you look at the p-value, this is the same as the p-value that we have seen in the ANOVA table when we used height as the second predictor variable. Thus, we can see that R automatically sequentially tests the single terms as and when they are added in the multiple regression models. The variable selection techniques using R can also be performed using the R function of REG subsets in the LEAPS package, but we will dedicate a separate module to studying the variable selection techniques using R. So in this module, we have learned how we can perform inference on a multiple linear regression model. We have seen how we can test the goodness of fit of the entire model, which includes all the independent variables taken together. We have also seen how we can test each independent variable whether they are significant or not, and also we have tested the nested models. We have seen if we drop a few independent variables how we can test the statistical significance of a model which contains a fewer independent variables in the model.